What specific problem does the Fourier head aim to solve in the context of large language models, and what gap in existing methods does it address?
The Fourier head aims to solve the problem of effectively modeling complex probability distributions in large language models, LLMs, by incorporating a continuous structure into the token classification process. Existing methods, such as the standard linear layer, treat token distributions as unstructured categorical distributions, failing to leverage the inherent similarities between nearby tokens, especially in non-linguistic contexts. The Fourier head addresses this gap by using Fourier series to learn a continuous probability density function, allowing for a more nuanced representation that captures low-frequency signals while penalizing overfitting to high-frequency noise. This design enables the Fourier head to better model multimodal distributions and improve performance in tasks like reinforcement learning and time series forecasting, as demonstrated by significant improvements in returns and forecasting accuracy over traditional methods. Thus, the Fourier head provides a more expressive and structured approach to token classification in LLMs, enhancing their ability to handle continuous data effectively.
How does the proposed Fourier head algorithm work? Illustrate the process step by step, including how it formulates the learned probability density function and generates discrete approximations.
The proposed Fourier head algorithm operates by taking an input vector, x in math bb_r, and processing it through a linear layer to extract coefficients for a Fourier series over the interval -1, 1. This series is defined with n frequencies, allowing it to model complex probability distributions. The interval -1, 1 is then quantized into m equal bins, and the Fourier head evaluates the learned Fourier probability density function (PDF) at the center points of these bins. The resulting evaluations yield m likelihoods, which are returned as a categorical distribution. This process enables the Fourier head to effectively capture the continuous structure of the data, while providing a discrete approximation that can be used for tasks such as classification or prediction.
Can you provide a concrete example demonstrating the Fourier head's implementation in a practical task, detailing how it compares to a linear classification head?
A concrete example of the Fourier head's implementation is illustrated in the task of beats per minute (BPM) classification for metronome-like audio samples. In this scenario, the BPMs are grouped into contiguous bins, such as 50-54 and 55-59, which have a natural continuous structure. The Fourier head was used as a drop-in replacement for a standard linear classification head in the audio spectrogram transformer, and it significantly outperformed the linear head, achieving an F1 score improvement of +118%. This success is attributed to the Fourier head's inductive bias of continuity, which allows it to learn smoother probability mass functions, PMFs, compared to the linear head. The results demonstrate that the Fourier head effectively captures the underlying continuous structure of the data, leading to better classification performance.
What are the primary theoretical or practical benefits of using the Fourier head over traditional linear layers in modeling distributions?
The primary theoretical benefit of using the Fourier head over traditional linear layers lies in its ability to incorporate continuous structures into the modeling of probability distributions, which is crucial for tasks where nearby tokens represent similar items. The Fourier head learns a continuous probability density function and outputs a discrete approximation, allowing it to better model low-frequency signals while penalizing overfitting to high-frequency noise. Practically, this results in improved performance, as demonstrated by a 46% increase in returns for an offline reinforcement learning agent in the Sequest game and A3. 5% improvement in zero-shot forecasting accuracy across 20 datasets. Additionally, the Fourier head's design allows for flexibility in modeling complex multimodal distributions, which traditional linear layers struggle to capture effectively. Overall, the Fourier head provides a more expressive and structured approach to probability density estimation, enhancing the model's generation performance in various tasks.
How was the effectiveness of the Fourier head validated in the experiments, and what metrics or benchmarks were used to demonstrate its performance improvements?
The effectiveness of the Fourier head was validated through experiments on two large-scale tasks: an offline reinforcement learning (RL) agent in the Atari game Sequest, and a time series forecasting benchmark. In the Sequest task, the Fourier head improved returns by 46% compared to a linear classification head, demonstrating its ability to model the action distribution more effectively by leveraging the continuity of similar actions. For the time series forecasting task, the Fourier head outperformed a state-of-the-art foundation model by 3.5% across 20 unseen datasets, indicating its superior performance in zero-shot forecasting. The metrics used to evaluate performance included mean reward totals for the RL task and accuracy metrics, such as mean squared error (MSE) for the time series task. Additionally, the smoothness of the learned probability mass functions (PMFs) was assessed, showing that the Fourier head produced smoother distributions than the linear head, aligning with the theoretical expectations outlined in the paper.
What limitations or challenges does the Fourier head face, particularly regarding the trade-off between the number of frequencies and smoothness of the predictions?
The Fourier head faces a significant challenge regarding the trade-off between the number of frequencies and the smoothness of its predictions. As outlined in the paper, increasing the number of Fourier coefficients enhances the expressive power of the model, allowing it to capture more complex distributions. However, this comes at the cost of smoothness, as a higher number of frequencies leads to a greater likelihood of fitting high-frequency noise, resulting in less smooth categorical distributions. The paper formalizes this trade-off through a scaling law, indicating that while more frequencies improve modeling capacity, they also degrade the smoothness of the learned distributions. Additionally, the implementation of Fourier regularization is necessary to mitigate overfitting to noise, but it does not completely eliminate the inherent trade-off between expressiveness and smoothness.